In this video, we're going to be looking at state changes and internal energy. So the fundamental diagram that's going to appear again and again in this unit is this diagram where we have temperature on the y-axis, and I suppose technically time is on the x-axis, but often it's not labelled. And then we have some substance, often water, that's being heated, melted, heated, boiled, and heated again. And we need to be really happy that we can teach students that the bottom bit here is where it's a solid, a liquid, and then a gas. And then this bit here is the state change of solid to liquid, which is obviously melting or freezing. And here it's boiling or condensing. Now there is a state change that goes from solid to gas, which is called sublimation, which students should know the name of, but they don't really need to know anything more. And if we go the other way, it's called deposition. You don't need to know that, students don't need to know that, but it's sometimes they ask, and virtually no student ever knows this. So from year 7 upwards, they'll probably be pretty confident drawing particle diagrams for solids, for liquids. Liquids should really be in a container because otherwise they would spread out, and the particles should really be touching, but there should be gaps between them. And then the gas, they are really far out, far apart. And sometimes we draw arrows on them to represent the fact that they're moving quite fast in random directions, but that's not crucial. So in a state change, the temperature remains constant. That is really important. Why is that? Because as we're going this way, what are we doing? We're breaking bonds. And here again, we're breaking bonds. And it takes energy to break the bonds. And then if we're going the other way, we're forming bonds, which effectively releases or gives out some energy. So what's happening in this bit here when the temperature is increasing? As the temperature increases, the molecules or the atoms or the particles gain kinetic energy. Here again, the particles being heated, or the substance being heated, the particles are gaining kinetic energy, and again up here they're gaining kinetic energy. In this section here and this section here, the bonds are being broken or forming if we're going the other way. So this leads us nicely to the definition of internal energy, which is a really simple concept, but a lot of students think it's harder than it actually is. So internal energy is defined as the sum of the kinetic energies and potential energies of the particles, or all the particles in a substance. So this is really simple, really. You know, if we have some substance, what is its total energy? Its total internal energy. It's a sum of any energy it has because of its temperature and its kinetic energy, and is also the sum of any energy it has because bonds have been broken, or effectively the potential energy. So the potential energy, really, we say it's due to its position. So often students will get a little bit confused with this idea of potential energy in this form. Right? One way is to say it's purely the energy that goes in to break the bonds, but then they might say, well, how can a solid have any potential energy? It has the least potential energy, but it's going to have some potential energy. So it's worthwhile using the analogy of GPE. So if we have a box on the ground, it's going to have some gravitational potential energy, and if we rise it up, it's going to gain potential energy. It's going to gain GPE, right? Because its height is increasing. So what we can say is the further this distance is, the more potential energy it has. So we can say the further the molecules are apart, the more potential energy they have. And obviously here they have a huge amount of potential to get close to each other. Here they only have a very small amount of potential to get close to each other. But because they're vibrating, all the time, they're not stationary, they're vibrating, there is going to be, tiny little gaps between them that will cause some potential energy. You should do lots of questions on this, lots of questions saying, what's going to change in terms of internal energy when you heat something up or when you do a state change, or you could even bring this idea in here. A really nice question to ask is if you have like a swimming pool full of water versus a cup of hot water, say, 100 degrees Celsius, which one has more internal energy? And often students will say that the cup has the most internal energy because it's the hottest, and that's their kind of basic level of understanding. But when we remind them that it's all the particles in a substance, then something with a massive volume, such as a swimming pool or an ocean, is going to have more internal energy overall because we're looking at the entire substance. We should also take students through several changes. So, for example, if we start up here and we cool it and then it condenses and it cools again, what's going to happen in each of these stages? Initially, the kinetic energy will decrease, then the potential energy will decrease, etc., etc., etc. And then finally, we should do lots of practice describing these states to students and getting them to practice, because there's very often 6-mark questions where they need to describe the arrangement of particles in a solid, a liquid, and a gas. And if you just describe these pictures, you're doing pretty well, really. We can see that they're close together. They are in neat, orderly rows. They're going to have the lowest potential energy, for example. They are going to be vibrating continuously because they will have some temperature. The liquid is obviously a bit more free to move. The bonds are slightly weaker between them, which is why they can flow. They take the shape of the container. And a gas, we have random motion. And when we say random motion in a gas, what we really mean is a random distribution of velocities, which means speed and direction. That's usually quite important, that the speeds have a distribution and the directions are all over the place. And then we can, if we want to extend students' knowledge, and this does sometimes come from exam questions, we can talk a little bit more detail about evaporation. So evaporation is not boiling. Evaporation happens at any temperature. Boiling is the state change that happens at a substance's boiling temperature. So, for example, water would be 100 degrees, whereas evaporation, a puddle will do that even on a cold day. So what happens when evaporation? We obviously have liquid is turning into gas, and we have only the most energetic molecules leaving. So if the most energetic molecules are leaving, anything that's left behind must have less energy. So what happens over time? What does evaporation cause? It causes cooling down, because it takes energy to make the most energetic particles leave, and the ones that left behind have lower energy. This often confuses students initially, but as soon as you say, well, what happens actually when you sweat, or what happens if you put water on you, and they go, yeah, of course they cool down. Or hand sanitizer, very topical at the moment, and they'll know that alcohol evaporates really easily and cools you down really, really quickly.